Swayam Prabha. Digital India. Educated India.
So, we are back to module 5, lecture 4. So, in the previous 3 modules of prefabricated concrete construction, we had tried to cover after the introductory lecture, then we moved to the precast items which we usually use in developing countries. We had in the first lecture discussed why we cannot adapt it so rapidly like other developed countries, and in the lecture 3 we had extensively discussed on the wall panel system, where we had understood that these are very intensive mechanized system with lot of precision to be placed in position one after other, and it is facing expansion. So, there should be proper sealing where it can actually take in some kind of, there is a cushion which is possible through the sealing system, and we could design. Now, we come to the floor panel part. Now, when we are coming to the floor panel part, we have to remember that these floor panels does not require any joining as such, which has to be watertight, which was required for the wall panel system, the masonry units or the aerated concrete units, whichever. Now, coming to the floor panel system, which is today's discussion, we see we have a system for the small spans, we have another set of system for the long spans, and this long span will also include the combined floor panel, where beam and slab it is together coming as a composite. And also we need to know the assembling system which I was referring to in case of wall panel or in case of the units which are quite larger in size as compared to the brick, the building units, they are set with mortars. The wall panels are set with sealants. So, here also we need to know what should be the assembling system when we are setting these panels one after the other. Now, coming to the small span system, this is adapted in our country context. As you see, a section of a small panel which is made of concrete with reinforcement inside it, which is a thin section compared to that of a cast in situ concrete floor. You can see the cross section here. So, if you cut a section through AA, you will see that the section is something like this, where the thickness you can find as 60 millimeter, which is smaller than that of a cast in situ system, and you see the reinforcement bars are inside it when it is fabricated. Now, what are these gaps doing? These gaps here, as you can see, they can actually pull the system, help taking the system to the place where it needs to be assembled. And if you look into the dimension, it is something around 5 feet, that is 1500, and on the other side it is only 1 feet. So, you can understand that this is humanly possible to be shifted to the place where it is to be placed. So, if you have such a small system and one after the other can be repeated, then you can create a floor where you can actually give load. So, you can see this section on the transverse side. Similarly, what you see on the other side, you see the longitudinal section. Now, here you will find that there is a detail. When one section comes and is placed after the other, there should be some supporting member. It may be a wall, it may be a beam. So, if it is a beam, you will see the beam is raised in position with a reinforcement bar coming out. So, when this is again a precast beam, where a reinforcement rod has been taken out. Why is it so? One is it is helping to lift the beam to position, and as you had seen that there is a rod inside it. So, a rod through and through passes through it to lift the beam entirely to the support system around it. I will come to that in the next slide. So, once this system beam is in position, you can actually lift individual units and place it one after the other. So, let us see it here. Here you see, if it is a small room of say 3 meters by 3 meters, and so if it is internally it is from here to here, it is 3 meters by 3 meters, 3 meters cross 3 meters. Then actually you can place 1, 2, 3, 4 units in this direction, 300 each and 1500 long, where this is the supporting beam. So, this supporting beam rests between the two walls, and the cross, it is the floor slab which is resting on one side on the wall groove, on the other side on the wall groove, and the other end resting on the beam, as you had seen in the previous slide. So, once this is done, you can now find out that this is how the section looks. So, you can see this is the transverse section, as you can check. This is the transverse section edge of each of the slab. What is happening? For lifting purpose, you had used this, you had made this notch, and there you are now filling some weak mortar to bring the entire floor in one particular level. So, you are putting some mortar, you are filling some mortar and bringing it, completing it or making it at one level, so that it can be used as a floor. As if you remember, I had shown you an image. So, this was from a model, this picture was taken from a model developed by BMTPC, Building Material Technology Promotion Center. Those who have developed for our low cost housings. It is a fast mechanism. You can create 3 meter by 3 meter rooms, one adjacent to the other, and you can make the roofing very quickly, even if the support is a brick wall. So, now here in this image you can see the mortar is being filled and the gaps are completed. What happens in case of the roof? In case of roof, water may enter through the gaps, narrow gaps here and there. So, a bitumen layer or an EPDM sheet, particularly used for damp proofing, may be inserted on the roof level. So, once that is done, the moisture entry or water entry can be controlled. So, this is extensively being used. Here you must remember, in a developing country like ours, we can use this system for low cost housing, small span structures. But on the other end, if we look into large constructions, industrial constructions, factories, there the span is not so small like 3.6 meters or say 3 meters, where we can adopt such small span system. Here we need to think how we need to cover longer, larger spans. Now these again are made of concrete. As I had told you in my introductory lecture, most of these units are concrete, made of concrete with reinforcement. As they are taking tension, there should be reinforcement inside to take the tension member, take the tensile load. So they are again made of early strength gain cement, that is quick setting cement, low slump concrete. These terms you know. Low slump concrete means it is stiff concrete, less of water in it. Steam curing for 24 hours, these are all factory made. Pretension steel wires can be used for larger, higher efficiency, larger spans, etc. So pretension is the wires or the reinforcement is put under tension before the casting is done. So they can take higher amount of load, tensile strength. Now under this long span we have two types. One is the slab only and other is combined or composite of slab and beam together. So coming to the slab, which is itself standalone slab, they are again of two types: flat slab, hollow core. So flat slab is 100% concrete with reinforcement inside it. Hollow slab is having cores spreaded along the entire, where it is reducing the weight, at the same time going for larger spans. Now you see how it is represented. FS is flat slab. F stands for flat and slab, 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 of which again you see 4 is the 4 feet of its width. So if you go by code, you will find FS4, that means it is 4 feet with flat slab. So it will not have any hollow core inside it, it is solid slab. Length can be as large as 25 feet. So you can now understand that we were talking of small spans, which was referring to something around 5 feet, and now it is, we can see the system is itself taking 25 feet in one go. Coming to the hollow core, it is represented by 4HC6, where actually 4 refers to the width, 4 refers to the width and 6 refers to the 6 inches in depth. So if you are referring to such code, you must remember that in flat slab it is ending with its width, whereas the hollow core slabs are beginning with its width and ending with its depth. So these are now available up to length of 40 feet and can vary up to a thickness of 200 millimeter. How are these cores made? You can have pipes inside very close set in the mold and then the casting is made. So, it is continuously cast in the industry and they are made hollow. Now, these hollow can have another advantage, can be the carrier of various service lines. So, some service lines may pass through these hollow cores. Next, coming to the combined beam column. These are having the beam associated with it. So, this is similar to flat slab with ribs. So, these ribs act as the beam and they are usually looking like the figure T. So, these will have large flanges or projections which will act as slab one after the other, and these ribs will act as the beam. Now, there are different types, double T, single T and waffle slab, where T is on both the directions and it becomes a waffle like structure. So, we will come to each of them one by one. These are sections through the solid core, that is flat slab, and the hollow core flat slab, hollow core slab. Now, what you can see here, similar to the small spans, here also there are grooves to have anchorage, and they are also helping in setting the concrete or mortar which will be added later to make it a single surface. So, here also you can see such grooves. You can see the reinforcement bars which are shown by black dots. So, they are all designed accordingly and are placed. So, after assembling, the gaps are filled with mortar after placing the units in position. This allows services pass through these holes, or sometimes the services are embedded in these gaps also. So, whenever two such members are sitting one after the other, you can actually have the service lines passing through, on top of which you can actually pour in the concrete. So, let us see how it looks when it is made in factory. So, this is a picture collected from the Shutterstock. You can see this is made in factory, how they are separated and kept in position. They are to be carried to the site, and each of them you can understand it is a huge length. Here you see another picture where you can see these grooves within the top part or the face, which help in lifting these in position. Now, you can see the grooves in the side for better anchorage of the mortar, and these are lifted at both ends by means of a crane and kept in position and kept over beams below. We will come to that later. So, they are not resting on brick walls, which we had seen in case of a small span floor slab. Here we are seeing it is sitting on a precast beam which is already in position. Now let us come to the combined kind of floor slab. What we see here, it is a double T as I was telling. This is a single T. You see with the double T, the rib size depth has gone down. Here it is a larger, single T is having a larger rib. So that is the web, that is the flange, and it is around 8 to 10 feet wide. Now these can sit over a system in the way it is shown here. There may be special notches at the end of the T. There may be special notches in the web to get into a walling system. So this is the continuous T which needs to get assembled in a walling system, where this will exactly go and match with the wall system. So one has to be very careful while these are being placed. These are all to be set within its groove if the drawing is perfectly done. So every instruction should be there when it is being fabricated, when it is being made, and when you are coming to site, it is only the job of assembling it in order where the way it was actually placed. So these webs or ribs of the floor plans rests in appropriate slots which are kept in the wall panel. Ribs have setbacks to get fixed in the wall. Thickness of the flange and the web depends on how big the span is and are specified in code. Even the reinforcement dimensions are specified in code. So we as architects, we need to know the system, how it needs to get into place, and then accordingly we have to design for the industrial structure, or say a large scale, large span office structure, office space, which will use these panels. So we need to get prepared, knowing these systems instead of only knowing the conventional methods. So when we are plunging into the prefabricated world, we have to follow specific rules, specific nomenclatures. We have to know the codes, what is the specification, and we just cannot make a wishful dimension. We have to look into how big this can go up to, and what is my requirement and which is the closest in dimension, and we have to design accordingly. So after looking into the different types of floor panels, both short span or small span as well as long span, let us try to also see the other one, which is the waffle slab. These are also meant for long spans, where you see it is one slab, it is not a flat slab, neither a T slab, neither a combined one, rather a combination of both. So these can go for large spans, but they can take in tension in both the directions. So they have ribs in both the directions and they have much better stability. They can be managed with much thin cross section. Here you see around 50 millimeter of slab thickness you can actually achieve. Here is the 50 millimeter slab thickness, and you can have the ribs or the webs of much lesser dimension. So charts are there accordingly the mold is now getting complicated. The reinforcement system inside it is also getting complicated, which was not that much difficult in case of the others. So, if such kind of slab is also adopted, you can go for such kind of slabs for long span. Let us now go to how these are to be assembled. Precast beams and precast girders. So, we use the girders when it is a large span. We can use these precast beams which we were talking about when we were also doing the small spans. Here these are to be of the length between the support system. So, here you can see this may be huge long rectangular beam, or it may be at the edge it may be L-shaped beam. Now, this L-shaped is having the projection where you can actually rest the slab. So, you can understand that there should be this dimension should be matching with the thickness of the slab. Now, in the case of the short span, you had seen the reinforcement is projecting out. Here also you see the reinforcements are projecting out in all the cases. What are they doing? When the slab is placed here, at the end these are to be locked, these are to be sealed. So, this area again another slab will come on the other side. So, these are to be sealed with mortar and a same level will be reached and the load sharing will take place. If it is a rectangular beam, you see it is RB, 16 inch refers to the width, 24 inch refers to the depth. So, there should be 16 inch, 24 inch. Similarly, you have L refers to the L-shaped beam, IT refers to the inverted T-beam. So, same way these charts are to be followed to get specific dimension for the particular thickness of slab. Now, this slab may be a flat slab, this slab may be a hollow core slab. So, depending on what the specification is, what is mentioned, the items are to be chosen, the depths and dimensions are to be chosen. So, these projected reinforcements help them to place in position. At the same time, they help to make it an unified structure when the mortar is put on as the final layer. Now, coming to the beam column slab connection. Here, when we are setting these columns, setting these slabs, hollow core slabs or the flat slab, you see we were placing it on top of these rectangular beams, say, or L-shaped beam. So, on rectangular beam you can see how it is set. It is set on two sides of the reinforcement. So, this is the reinforcement and you are setting your member hollow slab here, on the other side hollow slab there. So, the reinforcement is in between, and when you are coating it with the concrete, some concrete is getting filled here and the top is getting a fine layer. Here you see the beam has been welded to the column. What did we see when we were looking into the wall panel system? They were set one after the other with dowels one inserted within the other on the vertical direction. On the horizontal direction there were gaps where sealants were pushed into. There were backer rods to absorb the expansion if any, but here the load has to be transferred through the beam into the column. So that is why the beam cannot be unstable. It has to be set finely, rightly with the column. So the beam you may check it is sitting on the bearing pad, which is a projection in the column. That has also to be designed so that this projection is always left on that particular position. The beam is resting on it. Further, the beam is having welded connection with the column, making it a very strong joint. Thus, whatever load, some 30 feet, 25 feet, 40 feet, entire load is being borne by this and is transferred through the column to the foundation. If that is not done, the structure or the system will crumble. In case of cast in situ system, we do not have such options. There, beam, column, slab are altogether cast in one day and then it is left for curing. So there is a continuity between the entire structure. It becomes monolithic. Here that is not possible because you are assembling or integrating piece by piece. So this has to be kept in mind. So these bearing pads, steel angles, metal plates, all are to be there to take the load of the precast slab, and finally once everything is done, you are laying the concrete fill on top to give it a very neat finish which one cannot identify even what is the system below it. So we may conclude that depending on the span, the type of the flooring system has to be selected. Beam and column should be in place to receive the flooring member. So you just cannot start placing the floors without your beam column system in position. Beam column system may be precast, it may be steel section, it may be brick wall, it may be anything other than precast system also. Floor slabs are to be accommodated in the walling system also if it is a combined system. If it is not a combined system, it may be lying independently on the structural system, and then the walling may be done with even brick wall or concrete masonry units or aerated autoclaved concrete blocks. So with these we finish this lecture 4.